I want to continue characterizing the RSP spectrum analyzer. If you've watched the introduction or part one or both, you know that this spectrum analyzer is a piece of software that uses an RSP receiver, a RSP1, 1A, 2, 2 Duo, I think RSP2 Pro, anyway, the whole line of RSP receivers to as a hardware front end for a spectrum analyzer. And what I'm going to be doing in these experiments is in part one we looked at the basic capabilities and at how small a signal the RSP can detect and display, and we discovered that it was quite good. It has a very nice dynamic range. Now, I am not going to be trying to exceed the specifications of the SDR. Here are some of the specs, and you may notice that it has a 50 ohm input impedance. Its frequency range is 1 kilohertz to 2 gigahertz. The maximum input power is 0 dBm continuous and up to 10 plus 10 dBm for a short duration. We're going to stay below 0 dBm in all of these experiments. Now, I know some of you may like to see me drive it a little hard, maybe up to 10, to see what it will do. I'm not going to do that, partly because I don't want to encourage people to deliberately exceed the specs of a device. And people who are smart enough to to study this before they do something like that, or who already know how to use spectrum analyzers, they'll understand what they need to do to protect it. But for someone who just blindly jumps into this, I do not want them to say, well, Tom Tech Test said it was okay to put 50 dBm into my RSP. No, stick within the specs. Okay, with that caveat, what do we have on the bench? Well, the RSP receiver itself, and then next to it is a GRF 1300. It's a device made by Instec. It's a student trainer, and I've had this for quite some time. It was a fairly popular device, and it may still be used in some labs. The nice thing about this is its frequency range. It has both a baseband generator and an RF generator, as well as the baseband or the RF generator can be frequency modulated, and it also includes an AM mixer or modulator that allows you to do an AM signal out of this. It provides a variety of baseband frequencies and RF frequencies in the 800 to 900 megahertz band. Now, right now, I have it set to 900 megahertz out with a baseband frequency of 1 megahertz. Now, you can use either a sine, a triangle, or a square wave for the baseband. We are using a sine wave. And now I have the baseband signal connected to the RSP1, RSP1A. And on its input, I have a DC block, which is always a good idea, just to make sure you don't apply DC to the input of a spectrum analyzer. It's always a bad idea to do that. And then a 30 dB mini circuits attenuator to attenuate the signal. And once again, this is in part to protect the RSP1A, but it's also to provide some isolation from the output of this generator, because it cannot provide a lot of output power. So by putting this attenuator in place, we stabilize the input impedance of this device with regard to the generator. So let's take a look at what the spectrum analyzer shows us on this. Here we see the spectrum analyzer showing the spectrum of the baseband signal. Now remember, this is a 1 megahertz baseband. It's a sine wave, so we ought to just see one spike. Now I've adjusted the output for minus 40 indicated on the RSP. Remember, we have a 30 dB attenuator, so the actual output of the generator is minus 10 dBm, and then there's a 30 dB attenuation to produce minus 40. Notice that there are some harmonics in this, or spurious signals in this generator. This is the second and third harmonic of the 1 megahertz, and this is the 10th harmonic of the generator. At least I think that's what that is. Let's see what the frequency. That's a megahertz. That's about 2 megahertz. That's about 3 megahertz. And that's about, well, that's about 9 megahertz. So it's not the 10th harmonic of the signal. The 10th harmonic would be out here somewhere. So that is what the baseband signal looks like. Now, let me change the frequency to 2 megahertz. Restart the spectrum analyzer. Now you see we get a different spectrum. This is the 2 megahertz. There are some signals in here, but notice that we are getting about minus 80 dBm on this signal and about minus 83 or 4 on that one. Let me go back to a megahertz again. I have a software program that allows me to change these, so I have to set that up. And there you see is the, and notice that these spurious signals are below minus 90. So one of the reasons I do this is to show you that even with a sine wave, you don't get a pure tone. There's always some harmonics due to nonlinearities, and there is phase noise and other issues that if you have been in RF measurement for a while, you understand. If you don't, just realize that there's no such thing as a pure signal. Just that as you spend more money, you can buy better generators, and the better the generator, the smaller the spurious signals. Now what I'm going to do is change to a square wave, and I'm going to restart the generator. And you see here is the 1 megahertz. This is the second harmonic, 2. This is the third harmonic, 4th, 5th, 6th, 7th, 8th, 9th, and 10th harmonics. Let's look at the frequency of this one. Yeah, it's right at 10 megahertz. This is what a square wave is going to look like. And I'm going into this because later when we look at things like FM signals, we'll see that the spectral content of a signal, AM or FM, depends not just on the carrier frequency and its characteristics, but also on the baseband signal and the type of baseband signal. So in this case, we have a square wave. Square waves have some second harmonic energy, although really technically they shouldn't. But they should consist mostly or entirely of the fundamental and then all of the odd harmonics, 3rd, 5th, 7th, 9th, and so on. Notice that as we go up in frequency, the strength of the harmonic goes down. Notice that the second harmonic, the 4th harmonic, the 6th, the 8th, and the 10th, let me move this so you can see the top of that one, are all roughly the same. And that's because these are not characteristics of a square wave. This is simply an artifact in the generator and the spectrum analyzer combo. Now I have reconnected the generator to show the 900 megahertz carrier frequency. Notice that I have the generator sweeping from 885 megahertz to 935 megahertz. And one reason I wanted to show some of the frequency below is this is the 900 megahertz signal. Notice it's about minus 40 dB. Now remember, we still have the 30 dB attenuator in there. This, however, is what is called a subharmonic. It is a frequency of 895 megahertz, so 5 megahertz below. Why is that? Well, this particular generator uses a phase lock loop, and the reference oscillator is at 5 megahertz. So what you're seeing there is the reference oscillator that's used to refer the divided frequency. I won't get into PLL theory here, but those of you that know about PLLs know that you divide the output frequency by some number to get it close to the reference frequency, and then you use feedback to bring the output frequency to the reference frequency. Notice that this is around 890 megahertz. It's not quite, it's a little below that, but this is another subharmonic. And then we have a spurious signal at this point. Now, the reason that I'm showing you these things is so that you will know that sometimes you will see spurious signals. They can be caused by three sources. First, they can be caused by the generator you're using. They can also be caused by the measuring instrument itself. In other words, the input to the measuring instrument is causing mixing that produces spurious signals. And finally, it can be either in the device under test or due to external interference getting into the device under test. In other words, it can be if you have a lab, for example, with a lot of RF energy going around, that can get into the system. So source, sink, and external, including the device under test, are the sources of your spurious signals. So I just wanted to show you this spurious signal at 900 megahertz. Now what we're going to do is apply the baseband signal to this 900 megahertz carrier, and we're going to watch what happens here. Now I've made a few changes to the spectrum analyzer. Notice that the center frequency has now been moved to 900 megahertz. That's this carrier. If I turn the modulation off, you see that we just get the carrier. Now we will add FM modulation at a megahertz to this 900 megahertz signal. Notice what happens. You start producing sidebands a megahertz above and a megahertz below. You also produce a sideband 2 megahertz above and 2 megahertz below. Now remember, this is just a sine wave. An FM signal contains harmonics that are actually due to a Bessel function. If you want to know more about this, you should look at the series I did on spectrum analyzers a year and a half ago, in which I talk a lot about the basics of FM modulation and Bessel functions and things like that. But just if you already know that, you don't need to go back. If you don't know that and don't care to know that, then just take my word for it that this is common for FM signals. Now, if this were an AM signal, we would just get, and it were a completely linear system, we would only get one upper sideband and one lower sideband, and we would not have these extra signals. So notice that as we increase the amount of modulation, we can get to a point where, watch the carrier, it's actually going down here. And what is going on there is the sidebands, the modulation, is actually phasing out the carrier. Once again, if you look at Bessel functions, you'll understand what's going on here, but this is often used to measure FM deviation. In other words, what you do is you adjust the amount of deviation, the modulating signal, until you drive the carrier down to zero, and then you can simply look at a table and determine from that what the deviation of the FM signal is. We're not going to get into all of those details because we're mainly interested in how good this RSP1A works as a spectrum analyzer. So let's reduce the modulation again to a kind of minimum FM. What we're going to now do is increase the number of FFT bins to the max. Now it's going to get slower. There we are. But you'll notice that we are now getting a lot more detail than we were. Now we're going to go back to about let's say 16,000 bins. And you'll notice that the noise floor apparently got worse. That's actually an artifact of fast Fourier transforms that I won't really get into, but basically as you increase the resolution of an FFT, what you're doing is you're creating more and more bins to sort the frequencies into. And in doing so, that apparently causes the noise floor of the instrument to get better, but actually all that's happening is that it's an artifact. It's often called FFT gain. So here is at about 16. Let's go back to about 100,000 bins, and there you see a pretty good representation of the FM signal. Okay, now let's try the same thing with an AM signal. Now we have a 900 megahertz AM signal, that is a 900 megahertz carrier with a 1 megahertz modulating frequency, amplitude modulated. This is the upper sideband, lower sideband. Now, I will also point out, notice that there are some artifacts. There's one that shows up here. I'm not sure if that's from the generator or external, but I know this one is from the generator, or actually from the AM modulator, because it's not a perfect modulator. It has some nonlinearities that cause a small amount of FM modulation to occur. And so you see that we're getting basically the second harmonic of this modulating signal is also modulating the carrier at this point. Now let's go to a 2 megahertz modulating signal. And you see the sidebands move out to 2 megahertz on each side of the carrier. Once again, I'm not trying to teach a class in RF theory or modulation theory. We are using this to show how the RSP1A can be used, and I suspect that there will be some universities and technical schools that will probably adopt this software and the RSP1A or RSP2 in their RF teaching labs. I also hope that a group of radio amateurs and other interested people will be able to equip their lab or shop or whatever they call it with a spectrum analyzer, perhaps for the first time. The RSP1A costs around $100. I haven't looked lately at what the exact price is, but for about that price, you can get a pretty nice spectrum analyzer. It goes all the way to 2 gigahertz. And so this is a 2 megahertz sine wave modulating. Let's go to a square wave and see what happens. Well, it doesn't look like it made a big difference. Let's look more carefully at the carrier. Yeah, it doesn't seem to have made a difference, and that's good, because if there are no a square wave would make a difference if we were doing FM, but on an AM signal, the carrier and the modulating signal are separated by the fundamental. Let's look now at an FM. Here is a 1 megahertz modulating signal, FM modulating a 900 megahertz carrier, and as we saw before, you get these multiple sidebands due to FM. Now we're going to change the modulating signal from a sine wave to a square wave. Now you'll notice some interesting things going on here. So let's take a look at what that, and here is where some of the capabilities of this spectrum analyzer really come into bear. Now understand, expensive spectrum analyzers can do this as well, but for $100 I think this is incredible. Watch what we're going to do. First thing we're going to do is we're going to narrow the span down to just 2 megahertz. In other words, the carrier frequency plus or minus 1 megahertz. Now you see that there's a carrier, or there's a sideband down here, but we're mainly interested in what's going on with the carrier itself. And notice that what we are doing is creating sub sidebands due to the harmonics of the square wave. Now let's go in just a little further and look at about a megahertz, and then let's go to a higher resolution. And there you see let's go back to a megahertz. One of the problems that we're having here is that the generator and the spectrum analyzer are not completely on frequency. That's partly due to the generator. The generator is not an extremely precise one. It's nowhere near as precise as that HP generator that I was using in part 1. So this shows you the modulation of the, I think if we go to 900, there we are. That's a little better. And there you see we can zoom in on the signal and really look at the detail of what is being produced. It doesn't look very nice, does it? Well, that's partly because the modulator and the VCO in this trainer isn't an especially good one. You would not meet FCC broadcast specs, for example. But it does give us a really good idea of the capabilities of this RSP spectrum analyzer. As I said in part 1, and still true after part 2, I am very impressed with this. Now, I have ordered some parts that I hope to use with this in perhaps a part 3 to come. Once again, I ordered the parts from China. It takes forever to get that stuff, but if and when that, well, one part from Kiev and one part from China, or 2 parts from China and so on. At any rate, if and when that equipment comes in, it's very very low price. So the you basically pay the shipping, you get the device for free. I will do a part 3 on this using those new parts, but for now I'll keep that to myself. And I think that some of you who understand these areas probably know where I'm going, but at any rate, for this video, I think it may be time to kind of close this out by showing that we've demonstrated how you can use the RSP1A spectrum analyzer to examine various RF signals. In this case, a 900 megahertz trainer was used to generate AM and FM signals with varying basebands. Perhaps at some point in the future, I might do a part on decoding various digital modulations, or at least displaying digital modulations, things like binary phase shift keying, quadrature amplitude modulation, and so on. I did a whole series on that using the Signal Hound, but I suspect I'm not going to do that with the RSP simply because, unlike the Signal Hound, which has the Spike software to do digital demodulation, the RSP spectrum analyzer at this point is only a spectrum analyzer. That's lots, but it's not quite as capable as something like the Signal Hound with its Spike software. But it is a very nice piece of equipment. I hope this has been enjoyable and maybe you've learned something. I certainly have learned a little bit about the RSP and its capability, and I am impressed. So look forward to some more videos, maybe on this, maybe on something else. In the meantime, have a nice day.